So, good afternoon, everyone. Welcome to the week three of the live sessions on the course Design of Steel Structures. I am your TA, Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So, in last couple of weeks, we saw the introduction regarding the design of steel structures, and we also saw some of the important aspects within the design of steel structures, like what are the assumptions, what are the design codes, what are the different types of loads, how we have to do the calculation of different types of the loads. That those all things we saw in previous classes, and in last lecture also, in last week's lecture, we also saw saw the introduction regarding the connections also. In that we saw riveted connections and bolted connections. So if we remember in last class, we stop it at somewhere. What are the different types of rivets and what are the different types of joints, slab joints and butt joints. And so today, in today's class, we will be seeing what are the assumptions that are there for rivets. Okay. So the assumptions that are applicable to the riveted joints are as follows. So if we have a set of rivets that are connecting two members together, then we assume that the rivets are stressed equally. Like there will be any pattern of the riveting done in the riveted joint, but what the design assumption says is that we have to treat that all the rivets are being stressed equally. So either all the rivets are assumed to have equal level of bearing stress or equal level of shearing stress. Okay. uh, this is assumption is actually true if this assumption is actually true if the plates are considered to be rigid. So I will write for you people. The first assumption is actually rivets are assumed to be stressed equally. Okay. Rivets are assumed to be stressed equally. Okay. So what happens is when they are stressed equally, so all rivets are assumed to have same shear bearing capacity. Okay, then this assumption is valid when plates are assumed to be joined rigidly. Okay, so this is one of the first assumptions. And second important assumption is, so when we drive a rivet within an hole, so the design assumption says that the rivet hole is assumed to be filled completely by the rivet. Okay. um, and one of the important thing here is this assumption is also true when in the case of cold driven rivets, but in case of the hot rivet driven rivets, it is not true, as the rivets shrink diametrically on cooling. Okay. So second assumption is rivet hole is assumed to be filled completely. Okay, completely. True for cold driven rivets. Okay. Okay. Third assumption is what we do is we neglect the friction between. The plates. Friction between plates. Neglect the friction between plates. This is the third assumption. Okay. What is the fourth assumption? So fourth assumption is shear stress is assumed to be uniformly distributed over the gross cross-sectional area of the rivet. Okay. So fourth assumption is uniform shear stress distribution. Uniform shear stress distribution over gross cross section of rivet. Okay. So actually, the shear stress distribution is not uniform when the loads is in within the elastic range, but due to the ductility of the shear steel and the shear stress distribution tends to be uniform as the load approaches the ultimate load. Okay, it is there. Stress in the plate is assumed to be uniform. Okay, one another fifth assumption. Okay, plate is assumed to be uniform. Okay, is assumed to be uniform. And as I already told you that rivets transmit the loads only through shearing bearing. Bending is totally neglected. Okay. Sixth assumption is bending of rivets. Rivets is neglected. Okay. And seventh important assumption is bearing stress is uniform between the plates and rivets. Okay. Bearing stress. Bearing stress is uniform between plates and rivets. Okay. So there is bearing action between the rivets and the holes that are driven within the plates due to which the loads are transmitted. We assume that this bearing stress is uniform between bearing stress is uniform between plates and rivets. This is one seventh assumption. Okay. Then moving forward. So like here in the diagram I have shown you. So there is one load acting in this direction, one load acting in this direction. So these are were the initially configuration of the rivets like this, and this. So after deformation, uh, they have bended like this and this. So this is the deformation of the rivets. And one more thing, what is the shear stress distribution? Elastic shear stress distribution. So this is the pull from one side of the plate. This is another side of the plate. Okay. So this is a rivet driven here. So the elastic stress distribution is like this. Okay. And plastic stress distribution is since once it reaches the elastic limit here, then there is constant plastic stress. So that is shown by this. Okay. So this is sigma 80, and this will be your yield stress Fy, because after yielding plastic range begins. Okay, Fy. Okay. And one more thing is bending in rivets. If you see this joint, like one plate from this side, one plate from this side, and one plate from this side, P acts in this direction. So for reaction P by 2 acts in this direction. So if you consider this region here, that is shown here, P by 2 is acting along this, P by 2 is acting along this. We have P acting like this. So the resultant is so that actually eccentricity being 3/4 of T, okay, which is shown here, 3/4 of T. So moment will be equal to load multiplied by the lever arm, that is 3/8 of PT. So it will be, the bending moment that will act on this is 3/8 of PT. And here bearing stress on the rivet, okay. So this is the shank of the rivet like this. So there is all time bearing stress on this, like this region. So this is considered to be a uniform, to be, and it is assumed to be a rectangular distribution like this, okay, of diameter d, which is equal to the diameter of the shank, and t is the thickness of the plate, okay. So this is the bearing stress distribution within the shank of the rivet. This is the bending in the rivet, or these are the elastic stress distribution and plastic stress distribution within rivets, okay. So this was the basic thing about this. And one more thing is bending stress in lap joints. For example, uh, this is a one plate like this. It has deformed. It has deformed, and this is one another plate like this. It also has deformed. So the rivet has deformed like this. Its initial configuration was like this, but after the load has applied to it, it has deformed into this configuration. So it was P applied along this. So there will be some eccentricity E E is equal to KT. Okay, so we need not to go into detail of this eccentricity. It is a higher topic. Okay, and similarly the bending shears, bending stress distribution in butt joint. So for example, if we have one plate here, and one plate here, and they are joined by a rivet with butt joint, double cover butt joint. Okay, so on rivet like this, stress distribution will be like this from this side, stress distribution will be like from this side, and there will be this parabolic stress distribution at the middle of the shank, okay. I hope you people got this point, okay. So for our rivet joints, what the code allows, what are the permissible stresses within our rivets is, for like here in the table I have shown type of rivets, and what is the permissible axial tension, what is the permissible shear stress, and what is the permissible bearing stress for power driven rivets and power driven rivets. So I have told you already in the initial classes what is the difference between power driven rivet and hand driven rivet. For power driven rivet, it is 100 MPa, it's 100 MPa and 300 MPa in bearing. For hand driven rivet, similarly, it is 80 MPa in axial tension, 80, 80 MPa in shear, and 250 MPa in bearing. Okay. So, what are there? Now we will read about different specifications of this rivet. So, first is the diameter of the rivet. Okay, how we define the diameter of the rivet as is it is actually the gross diameter, and it may be formed by increasing the nominal diameter phi. So, if we take nominal diameter, okay, nominal dia is equal to phi, we have to increase it by certain allowances. So gross diameter, GD will be equal to nominal diameter plus 1.5. These are clearance. Okay, 1.5 is clearance. Okay, it is for diameter of the rivet to be less or equal to 25 mm, and for greater than 25 mm, nominal diameter is equal to gross diameter is equal to nominal diameter plus 2 mm. Okay, I hope this point is clear to you. Then there is one more concept is gauge. What is gauge is, it is actually the distance between the adjacent rivet lines. Okay, if there are two rivet lines, the distance between the two adjacent rivet lines, or the distance between the back of the roller section and the first rivet line. Okay, or the center to center distance between the two consecutive rivets measured along the width of the member or connection. Okay, the gauge lines are specified on the section stabilized in it. So in this, where wait, I will show you what we call gauge. So for example, mm, so for example we have one, sorry, we have one angle section like this. Okay, so it is like this. From this side it is like this. Okay, okay, from this it is continuous like this. Okay, we have driven some sorry, we have driven some rivets into it. So there is one rivet line like this. There is one rivet more here. There is one more rivet here. There is one more rivet here. Okay, there is this is in staggered pattern. There is one more rivet here, one more rivet here, one more rivet here. Okay, so if I draw a line, this is rivet line one. This is rivet line two. So if you find the distance between the two rivet lines, okay, this is known as gauge. Okay, gauge length. Or if you see that it is actually the distance between the two rivets measured around the width. This is the width of the member, no? This is the width of the member. It is the distance measured along the width of the member, so we called it as gauge. Okay, I hope this is clear. And this is acted by some forces. Okay, P from this side and P from this side. This is a side view, and if we see one more view of this angle section from this side, if we see, so this is the side view. So this rivet line will come to this point. So this rivet line will be shown like this, and this rivet line will be shown like this from one side view, top side view. So we can call this as gauge. Okay, that is why I defined it by it is actually the distance. Okay, let me. It is actually the distance between the adjacent rivet lines. Okay, the adjacent rivet lines, or the distance between the back of a rolled section and the first rivet line. Back of a rolled section. This is the back of a rolled section from this, or this is the back of a rolled section from this. Or distance between back of a rolled section and first rivet line is known as gauge. Okay, or it has one more division, or center to center distance between two consecutive rivets measured along the width of the member. So this is the width of the member measured along this line. What is the center to center distance between two rivets? It is known as gauge. Okay, the gauge lines. Okay, I have shown here. So another important thing is the pitch. So pitch of the rivet. What is actually the pitch of the rivet? Pitch of the rivet may be defined as the distance between the center of two consecutive rivets measured along the row of the rivets, as shown in figure. Okay. Uh, so if we see that a row of the rivets, okay. So this is so this is the row of rivet. Okay. So let me write. So this is rivet row. Okay. Row. The center to center distance between two rivets along the row of a along the rivet row is known as pitch. Okay, we can call this distance as pitch. Okay, so I told you this in the definition. So uh, and what is the definition of the row actually is a row generally refers to a line of rivets placed parallel to the stress in a member. So member is stressed along this direction. Okay, along this direction. So the rivet line parallel to it. These are the rivet lines parallel to it. So these will be the rivet rows actually. Okay, I hope this is clear to you. So there are reasons why we give this pitch is that to prevent the tension failure of the members between two consecutive rivets. Okay, to permit efficient installation of the rivet. So this pitch is given. This pitch is given to have permanent efficient installation of these rivets. Okay, and one more thing is to prevent tension failure of members between two consecutive rivets. Okay, so, for example, if this rivet is placed very near to it, so there will be holes everywhere on the plate. So there will be the tension failure when they are being pulled from both the directions. So, in order to provide some material or some space between the two consecutive rivets, we give the pitch distance so that our member should not fail within tension. Okay, this is the example of this is the pitch definition of the pitch. Okay, moving forward, moving forward, we have okay. Then there are definitions. There is one thing is there is one more thing is edge distance. Okay, okay. First, there are the limits on this pitch. What is the minimum pitch and the maximum pitch? The distance between the center of the hole should not be less than 2.5 times the nominal diameter. So, minimum pitch should not be less than 2.5 times diameter of the rivet. Okay, so it is the limitation on the minimum pitch. So it is given because if the rivets are spaced closer, so there will be very less clearance left between the last formed rivet head and the die forming the next rivet head. Exactly. So if these rivets are placed very close to each other, so I have driven this rivet first initially. Then if I drive one more rivet to it, I won't be having space to hammer this rivet and to form a rivet head on this side as well. So to have enough space for forming rivet heads and to place these rivets efficiently, we have to give at least minimum pitch, which should not be less than 25 times the diameter of the rivet. Okay. So there is one more limitation on it is the maximum pitch. Okay, maximum pitch. So maximum pitch, it should be there. There should be a distance, or there should be an uh, restriction on the maximum pitch. So the distance between the center of two consecutive rivets in the direction of the stress should not exceed. It should not be greater than 16 times the thickness of the plate or 200 mm. Okay, 16 times the thickness of the plate or 200 mm, whichever is less. Okay, whichever is less. Okay, uh, less in tension members. This is for tension members in tension. Okay, so in compression there is different. There is 12T or 200 mm, whichever is less in compression. Okay, so this is the maximum pitch to be given. Okay, then there is one more thing is edge distance. This is the distance. Okay, edge distance. Edge distance is actually the distance from the center of the rivet hole to the adjacent edge of the member. So here we see if this is the center of the rivet hole and this is the edge, adjacent edge, the distance, this is called the edge distance. Okay, I will mark it here. Okay, this is called the edge distance. Okay, this is called the edge distance. So the purpose of giving this edge distance is actually the it prevents the failure of the plate in tension. Okay, the steel of the plate opposite to the hole may bulge out and may crack. This is the reason why we give the edge distance. Okay, then we have to in order to design a riveted joint we have to analyze it first and to determine its strength. So strength of a riveted joint. Okay, so let me explain this topic to you, how we determine the strength of a riveted joint. Okay, so strength of the riveted joint. First strength is the strength of rivet shear. Okay, Strength of rivet in shear. Strength of rivet in shear. Okay. So how we determine it? So uh, so first, the resistance of the rivet to shear depends upon the cross-sectional area of the shank and the allowable unit shear stress per rivet metal. Okay. So let me denote PS, strength of riveted joint. Okay. Strength of riveted joint. Okay. I am writing riveted joint in short form RJ. Okay. And let D equals gross diameter. Okay. Force is in Newton and dias are in mm. Okay. And let TVF, permissible shear stress on rivet. Okay. Permissible shear stress on rivet. Okay. And this is in megapascal. Okay. Then N is equal to number of rivets on each side of joint. Okay. Number of rivets on each side of joint. And one more thing is N dash, number of rivets in one pitch length. Okay. So shear strength of rivet.
Yeah.
Okay. Strength of rivet in shear. Okay. Strength of rivet in shear. How it is given as? It is cross area multiplied by permissible shear stress. Okay. This is for one rivet. Okay. Single shear. Permissible shear stress. So I told you in earlier classes there are two cases, single shear and double shear. So in first single shear we will see strength of one rivet. Okay. One rivet. So cross sectional area is pi by 4 diameter square times TVF, permissible shear stress. Okay. So what will be the total strength of joint? Strength of riveted joint will be total number of joint riveters multiplied by the strength of one rivet, n pi by 4 d square TVF, tau VF. Okay. Strength of riveted joint. So uh, so strength of riveted joint per pitch length. Okay. Per pitch length. For that we have to multiply by number of rivets per joint per pitch length. Okay. That is n dash pi by 4 d square tau VF. Okay. That is there. Okay. So double shear, we have to only multiply the single shear values by 2. Okay. So strength of one rivet is equal to 2 times pi by 4 d square tau VF, and other things will follow like this. Okay. And riveted joint, strength of riveted joint will be 2 n pi by 4 d square tau VF. Okay. And strength of riveted joint per pitch length. Okay. Length is equal to 2 n dash pi by 4 d square tau VF. Okay. It is there. Okay. So we saw in shear. Similarly, we have to see in bearing. Okay. So strength of rivet in bearing. Second is, anyone wants to ask something? Then please mute your mics. Okay. So strength of rivet in bearing. Okay. So in bearing we have to see the strength of rivet as also. So what is the bearing stress, bearing strength? It is actually the strength of a rivet. Bearing strength, it is actually the force that can be exerted on it by the section through which it passes. So for example, this is the hole that is there, and then we have a rivet inside it like this. Like this we have rivet inside it. So whatever the force that the section that is all over around it, that this force that is being exerted by the section around it on this rivet is known as the strength, bearing strength of the rivet. Whatever force that it can resist is known as the bearing strength of the rivet. So for that we have to denote different notations. So for if I denote PB, bearing strength of one rivet, okay, bearing strength, bearing strength, and again d gross diameter, t thickness of plate, thickness of joint, actually this is not plate, and sigma pf is permissible, permissible bearing stress, okay. And again n, total number of rivets, and again n dash, total number of rivets per pitch length. So similarly, whatever we did in shear, we have to do the same exercise here.
Sir, what is N dash, sir?
N dash is the N dash is the total number of the rivets per pitch length. Okay. So for example, we have one joint here, another joint here, another plate here. So we are attaching rivets like this. So if it is having pitch like this, so whatever will be the number of rivets that are coming into within this pitch length, so that is known as n dash. It's along the stretch direction like this. This is the row of the rivets. Okay,
Okay, sir.
you got the point.
Yes, sir.
Yeah. So that is per pitch length. Okay. Similarly, what we did in shear, we have to do here. Strength of rivet in bearing. Okay. Strength of one rivet. Okay. So actually, it is actually the projected area multiplies by the permissible bearing stress of rivet. Okay. So projected area is, I showed you somewhere. Here I showed you in bearing stress. Okay. So actually this is the rivet like this. This is the projected area, like the triangular projected area. That is d times the thickness. Okay. D times this is the projected area. Okay. D times the thickness. So we have to take that only. Okay. So that is actually d times t times sigma pf. Okay, so then the strength of joint will be ndt, because there are n number of rivets, ndt sigma pf. So it's very easy. Strength of joint per pitch like it. We don't have to multiply by n, we have to multiply by n dash, ndt sigma pf. Very easy. These are very easy formulas. Okay, you can remember these formulas. This is also one more formula. Okay. Similarly, we have to see the strength of the rivet within bearing. Okay, within tearing. Okay, sorry, bearing we did shear, we did bearing. Now we have to see this tearing. Okay, strength of rivet in tearing. Okay, okay. So what we have to see is, for example, our section is like this. This is our plate. Okay, it has rivets driven like this. I have, sorry, let me take a picture from this. I will take a picture from book. Yeah, we have this. In tearing, we have this picture. So in tearing, this is the plate. Okay, this is actually its thickness. This is its thickness, and this is totally what is the length of this side now. So if there are n number of rivets, like 1, 2, 3, so it is n. So total, what will be the total breadth available? So it was having initially b breadth. So there are n number of diameters that has been cut from it. So the effective breadth will be b minus nd. Are you getting my point? Exactly, it will be b minus nd. So we have to again denote the different things that we denoted earlier in bearing and shear. So here again let PT tearing strength. Okay, tearing strength. Let S be the pitch. Okay, pitch of rivets. Okay. Mm, B width of plate. Width of plate and number of rivets in section. Okay, number of rivets in section. D gross diameter. Okay, D gross diameter and sigma AT permissible tensile stress in plate. Okay, stress in plate. Okay, which is actually given as 0.6 of yield stress. Okay, Fy. So strength of the joint at critical section. Okay, strength in tearing at critical section. So strength in tearing will be, that is PT will be equal to net area multiplied by permissible tensile. Permissible tensile strength. Okay, so net area here is actually thickness multiplied by B minus ND. Okay, this is this area actually that I am highlighting. Okay, this area B minus ND. So it will be equal to B minus ND times thickness. This is the area, and permissible tensile strength is sigma AT. Okay, so if we see for per pitch, strength in tearing per pitch. Okay, per pitch length. So per pitch length actually, so if this is the pitch like this distance is pitch, one rivet will come into that. This is one rivet. So it is one diameter will be minus it. So it will be S minus D times T will be the total area. So what will be the strength of tearing per pitch? It will be out of B minus ND we have to write S. There is only one rivet, N will be one. S minus uh, S minus D times T sigma 80. Okay, per pitch. So this is the strength of the riveted joint in tearing. Okay. Then moving forward, then we have rivet value. Rivet value RV. Okay. What is this rivet value? So, for example, if we consider any section and we consider a joint in that, then we found the strength of the joint in all the three scenarios. That is either in shear or either in bearing, sorry, shear or bearing or tearing. Okay, we get the strength of the joint in all the three scenarios. Whatever will be the minimum out of them will be the rivet value. Okay, minimum will be the rivet value. That is why we define it as uh, uh, the minimum strength of a rivet either in shear or in bearing or tearing is called the rivet value. Okay, and efficiency of riveted joint, another important thing. Efficiency of riveted joint. Efficiency, this is given as efficiency neta is given as strength of riveted joint divided by strength of solid plate times 100. Okay, there is one more important definition, that is the net section. We define net section as it is actually the section available to resist shear after the holes of the rivets are made. Okay, so whatever will be total section to resist loads after holes are made. Okay, made is known as net section. Okay, actually, the rivets may be placed in a variety of patterns, and it depends upon the space available for the connection, as well as it depends upon the shape of the member to be connected. Okay, there are different types of riveting. The most common type of riveting patterns is chain riveting. There are some other patterns like diamond riveting and staggered diamond riveting. Uh, there in chain we have staggered chain riveting and staggered diamond riveting. Okay, so net section. There is different patterns of riveting. So one is chain riveting, another is diamond riveting. Okay, so I have shown here when the rivets are placed in the rows like this, like a chain, we call it as chain riveting. Okay, And when these same rivets are placed like very less at the extremes and more rivets in the middle, this is called diamond riveting. It forms like shape like a diamond. Okay, they and when the in chain riveting, if the rivets are placed in same line like this, it is known as simple chain riveting. But if they are placed in a staggered fashion like this, and like this is known as staggered riveting. So like this rivet is here, then there is no rivet here. There is skipping this, there is another rivet here. For this, the rivet is here. So this is staggered like this, okay? And in chain riveting, it is like straight. So this is chain riveting, this is staggered chain riveting. Same in diamond. This is diamond riveting, like same in same row like this, and but there is staggered diamond riveting like this. Okay, loads are being applied like this. This is staggered diamond riveting. These are the four types of riveting patterns. One, two, chain riveting, staggered riveting. Third, diamond riveting, and fourth is diamond staggered riveting. Okay. So now there is the design of concentric riveted joint. So actually, uh, why it is concentric riveted joint is like that. There is no eccentricity in the riveted joint, and the bending stresses are bending is assumed to be negligible. There is no bending within that. So what we call a concentric riveted joint is actually that rivet joint when the line of action of the load constant is at the center of the gravity of the rivet group. The joint is said to be concentric. Okay. So for example, there are sorry there are two members joined like this. Okay. There are two members joined like this. So for example, this is some rivets and their CG lies here. Okay, this is center of gravity of the riveted pattern. Okay, and this is the line of action of force P. So if they are along the same line, if they are along the same line such that eccentricity is equal to zero, then we call that riveted joint as concentric riveted joint. Okay, so it is important because after this there is no eccentricity, so there will be no bending on the riveted joint. A concentric riveted joint design consists of finding out the so in design we need to find out the diameter, we need to find the number or the pitch of the rivets and the efficiency of the joint. So let us start. So for example, we are in design problems, we will be usually given the thickness of the plates and we have to the thickness of the plate and they will be saying that either use lap joint and butt joint. We have to find the diameter of the rivets and the number of rivets that are to be required. So for the diameter of the rivets, for what we would do is initially diameter of rivets. So we put an initial guess on the diameter of the rivets using Unwin's formula. Okay, formula. So what does Unwin's formula say is that assume that the diameter of the rivet, that is nominal diameter, is equal to 6.01 times the square root of t, where t is in mm. Okay. So if we take this diameter always, we get a conservative design. So we will be always on the safer side, whatever diameter we have taken for the design of our riveted joint, concentric riveted joint, actually. Okay, from this diameter phi, then we have to calculate the number of the number and the pitch of the rivet. The number of rivets can be computed by dividing the total load to be transferred by the rivet value. So we found the diameter, okay, phi diameter from Unwin's formula. From phi, we will compute pi by 4d square times either tau vf, sigma at, these values. Tau vf, sigma at, or what is there? Sigma pf, okay? Sigma pf, okay? We will calculate the strength of the rivet in shearing Shearing, tearing, and bearing. Okay, we will take the minimum one. Minimum of them will give rivet value. So therefore, number of rivets will be equal to what will be the load transmitted by joint divided by the rivet value. Okay, we will solve one numerical problem on this so that you can easily get whatever I am talking. Okay, then we will calculate all the different values, that the efficiency of the joint and other things. So let me take you directly to the example problem. Okay, from that you will get a clear indication. So actually, what is the problem one for today is calculate the value of the rivet in lap joint. Use it to connect to two plates 12 thick. Okay, so we have given T is equal to 12 Okay, uh, for the following cases. There are power driven rivets and there are hand driven rivets. So in code, there are two different specifications for power driven rivets as well as hand driven rivets. So I told you what you have to do for. So first, let me make this for you people so that you will better understand. So these are rivets to be placed on this. Okay, T is 12 So nominal diameter. Okay, using Unwin's formula, it will be 5 will be equal to 6.01 root T. So this is 6 this is 6 so total T is equal to 12 Okay, T will be equal to 6.01 root 12. Okay, this comes out to be 20.8, which is conservative design will be 20 Okay, 20 we will take the nominal diameter. So I told you how to calculate the gross diameter. We will assume a clearance of 1.5 Okay, gross diameter. Okay, gross diameter 5 gross will be equal to clear with a clearance of 1.5 plus 1.5, it is 21.5 Okay, we have to take. And for case A, that is power driven rivets. For power driven rivets, if you see the code, the shear strength of power driven rivets tau vf is equal to 100 megapascal. Okay, 100 newton per square, and bearing strength is sigma pf 300 newton per square. Okay, or 300 megapascal. So strength in shear, if you put all the values, that is pi by 4 d square tau vf. If you put all the values, you will get it equal to 36.305 kilonewton. Okay, similarly in bearing, strength in bearing, you have to put pi by 4 d square uh, p sigma pf, sorry, sigma pf, which comes out to be 77 kilonewton. So minimum of the two we have to take, that is 36 Newton. So rivet value RV comes out to be 36.305 kilonewton. Okay. So moving forward, uh, what we have to calculate the value of a rivet. So rivet value we calculate for power driven rivets. So for hand driven rivets, there are different values. So for hand driven rivets, actually tau vf is little less, it is 80 newton per square, and bearing stress is also less, this is 50 less to 50 newton per square. So strength in shear comes out to be pi by 4 d square sigma pf, or pi by 4 t square tau vf. Minimum of these two we will take to be rivet value. So this comes out to be 64 kilonewton. This comes out to be 29 kilonewton. So the rivet value in for hand driven rivets comes out to be 29.04 kilonewton. So from this you calculate the rivet values. Okay. So rivet value is actually the value of the strength of the rivet either in shear or bearing, and minimum of the two. So I have kept a example 2 here. A 6 mm thick angle section is jointed by 10 mm thin gusset plate. The angle is supported by a load of P is equal to 55 kilonewton. Okay. Find out our number of 16 mm diameter power driven rivet. So power driven rivet, so tau VF is equal to 100 MPa, and sigma PF is equal to 2, 200 MPa, 300 MPa, 300 MPa. So you will calculate the rivet value is called to either pi by 4 d square tau VF, pi by 4 d square sigma PF, and you will take the minimum, okay, minimum value. Then you will get the number of rivets to be equal to number of rivets to be equal to load 55 into 10 power 3 kilonewton divided by the rivet value. Okay, so this is your homework. Okay, so you have given a gross diameter of 16 mm. Okay, no, only nominal diameter. Gross diameter, take a clearance of 16 plus 1.5. Okay, and now do this at your side. Thank you everyone for joining the session. The time is over. Thank you. I hope you enjoyed this session and you got the point regarding the riveted joints. So today we saw the design of the riveted joints and the type of the riveting and all the other things, strength of the rivets in different cases. Okay. I hope you people enjoyed this section. Thank you everyone for joining. You people can leave.